Right, good afternoon, everyone. Before we start our study of friction today, or before we get introduced to friction, I'd like to go back over what we had looked at prior in the last lecture, quickly, concepts that we will need, namely those of an inertial and a non-inertial frame. Remember we were speaking about that for a test mass, the coordinate system or the inertial frame, the frame of reference, can be taken as that of the mass itself. So if that mass is undergoing no external force and has a constant momentum, then it is in an inertial state. We also saw that if there was an external force on that particle and its momentum was changing, then that constitutes a non-inertial state. That constitutes the mass being in a non-inertial state. This led to a definition of mass, a convenient one at that, being a measure, a loose measure of a body's or an object's resistance to an inertial state change. And from there, Newton's laws fell out, single, double, and triple I here. Number one being the law of inertia, namely that a particle will remain unperturbed in an inertial state, and that is inclusive of a rest state, which of course is a constant momentum for a value equal to 0. Now, in order to transform it from an inertial to a non-inertial state, you go to Newton's double I law, second law here. The summation of forces here, indicated by the running index I, starting from 1 to n, where this is the number of forces on the particle, or the test mass, is equal to mass times acceleration. First time derivative of velocity, of course, as we know from calculus, and this is equal to the net force. If this net force is 0, then we're back to an inertial state, of course. We're back to an equilibrium, a mechanical equilibrium, a Newtonian equilibrium. If F net is greater than 0, we have an acceleration. If it's less than 0, we have a deceleration. And of course, triple I law corresponding to the third law. The force on I from J is equal to the negative of the force of J on I. This is a statement of the law of action and reaction. All right, so with that in hand, now that we have this out of the way, let's go to friction. Friction is actually a microscopic phenomenon, and I will make a comment about it here, but we will treat it as a macroscopic phenomenon. We'll treat this phenomenologically to begin with. So, on the subatomic level, no surface is smooth. This is friction stems from an interlocking of atomic and molecular bonds at the interface of two surfaces, one being a rest surface, for example. Or in other words, the surface upon which, taking the simple case, that a mass is resting, all right, or up against, right? This would be the surface. And of course, this is the mass m, right? Now, the interface along here, this interface on the atomic and molecular level has to do with this is an interlocking at the surface, and it increases as a function of how heavy or how massive this test object is. All right. So now, what do we mean by this, and how can we exploit this to get an idea of what friction is? Macroscopically, let's go with a definition for the moment. This will be denoted S and K, where these are frictional forces, and they have an index static, being for S, and kinetic being that for, of course, kinetic, K being kinetic. Let's sum the forces for a moment. Now that we have this nomenclature, let's sum the forces. Let's first look at it. Let's look at a sum in the x direction and a sum in the y direction, right? Where our coordinate system will be denoted the unit vector j hat for the y direction, and the unit vector I hat for the x direction, Now, if we sum the forces along x, right? Let's say that we bring in an applied, and there will be a resistance here that is known as the frictional force. That frictional force is stemming and is going to be equal and opposite, so long as the object is not moving, to the magnitude of the applied force. Now, summing that up, we've got FAPP minus FS I hat is equal to 0, so long as there's no motion. This is the case for a motionless system. So this is still inertial. Some of the forces in the y direction, you've got mg down, right, plus the normal force upward. Now this is unit vector j equal to 0. What do we have here? This is the normal force in this direction. That is the force from the surface on the block itself. Okay? The surface, or rather the force from the surface on the block itself. mg down is, of course, the weight of the object resting on this entire surface. And for the present case, this is motionless. This is motionless. Now, let me write here. Let me further write mathematically. For the magnitude of the static frictional force, you have a dimensionless quantity, mu sub s, which is known as the coefficient of static friction. This is times the normal force. Coefficient of kinetic friction is, of course, mu sub k, which is also a dimensionless number. And in general, mu sub k is less than mu sub s. In other words, the coefficient of kinetic friction is less than that for the static. What does this actually look like on a plot? Before we do any, suppose we draw. Let's take a look at a plot in time. Of the frictional force. And let's denote this point as being the max point, or the max frictional force, the threshold corresponding to this time, which I'll call T sub B, and I'll denote that later. Let's define this maximum frictional force as being that threshold beyond which an applied force will set the object in motion. In other words, the point at which there is a transformation from an inertial to a non-inertial state. What typically happens is that at that point where F applied, let me write here, F applied is for T less than TB, where this TB here, this TB, I'm going to define as breakaway. In other words, the point, the time, the temporal point at which, let's call this T0, the temporal point at which the applied force will overcome the frictional force. Notice this static frictional force rises in unison with a rising applied force until it reaches the breakaway point, at which time what typically happens is that the frictional force drops and then it remains relatively constant, where this regime is now that of the kinetic frictional force. To the left here, this is all static. So given that, you can see that in this regime, you have a non-inertial state. In other words, for F applied at TB less than, let me call this TB prime. For T greater than TB and less than TB prime, what we have now is a non-inertial state. I'll just write non in for now. This is a non-inertial state. For T, for F of AB, for T less than TB, it's an inertial state in this regime. From here over, this is inertial, no motion. Here, it's a non-inertial state. The object is now moving but decelerating. And to the right here, it will depend, this will depend on whether the applied force remains greater than the frictional force or not. So returning back to Newton's laws, the sum of the forces in the x direction gave us F applied minus Fk. Now we're looking at this point for TB prime, for T greater than TB prime. J, and this is MA. Now, in this, I should write, I'm afraid I don't have much room here, but let me. FAPP minus FK. Okay. If this is less than 0, right, then this is decelerating. If this is equal to 0, we have an inertial state. If this is greater than 0, then it's accelerating. This is in the regime to the right of TB prime. So we're talking about F T greater than TB prime. So this gives us some phenomenological feel. This gives us a flavor in general of what happens for a system in which you have a mass on a surface, just your run-of-the-mill mass, say a block of wood. And as you apply force, the object does not move right away. The object has some resistance, and that resistance, of course, is proportional to the mass of the object itself. So in this case, in fact, in every case we'll see, remember that this F of K is indeed mu K F normal, which is mu K mg. Right. So again, the mass looms. The more massive the part, the more massive this object is, the greater the frictional force, and the more force you'll have to apply to actually get it moving. So, even though there are no numbers here, this gives us a start, or gives you a feel of what is happening in these regimes. And what we will do now is we'll do some specific problems or examples with some numbers. And then we'll come back to the idea, or we'll come back to the case where the frictional forces are not necessarily constant, but are rather a function of velocity. So we'll have a look at that.